So welcome everybody. I hope you've had a good couple of days at ISPE here. And what we're going to go to today is as simple as it is, adding AI to pharmaceutical manufacturing. So I'm Vinod Rodriguez. I'm part of the Quartic team here at ISPE. And much of my experience and background has been in data science consulting. I've worked with data science teams in pharmaceutical companies and enterprises and worked with them to be able to develop AI solutions, ML modeling, analytical solutions that we could package and basically send out into a production environment or into a validated environment. So, what do we do at Quartic? Well, firstly, what we do is we change the way we want to implement AI into manufacturing. We want to be able to put AI not just into every data scientist or any kind of data science team. We want the process engineers, we want the SMEs to really take a hold of AI. That's our entire value at Quartic. We find much of the data science toolboxes can obviously be automated, can obviously be packaged in a very clean solution, but the knowledge really stems from your process engineer, from your SME, the people that have been working with the processes for the past 10 to 15 years. That's where all that knowledge is captured, and that context, more importantly, is captured, and that's what we with the Quartic platform would like to do. So I'm sure this has been thrown around a lot. Everybody always says you need big data, you need clean data, you need a lot more data. We'd like to argue something slightly different. What we're arguing is saying we don't necessarily need more data. You just need to maybe ask better questions. And the reason of that is, well, you can look at data multiple different ways. You can formulate your question and your perspective from multiple different points, from a quality point, from an engineering point, from a process point. All those things don't necessarily need different data and more data. They just need to be viewed differently. So with the Quartic platform, we're going to go through a few demos basically, and we're going to see how we can look at this. What we're quickly going to do is baseline the health and performance of your assets with existing sensors on data set we have today. The way the platform is built is you can connect to basically any kind of data historian database, DCS system, and you can monitor your assets real time. You can monitor your process, you can expand up and down the enterprise as you need. So what we're going to do is look through a data set. We're going to hopefully get some feedback from the crowd here, and we can see what best we can do with our knowledge. So, our example is going to be a bioreactor example, because if you're not doing something with bioreactors, you're not doing any intelligence at all, apparently, right? So, what we're going to do is not ask the typical question. I'm sure if you've got some sort of bioreactor process or fermentation process, most times or another you're going to say, how do I optimize this? How do I increase this yield? How do I increase this output from here? How do I reduce the amount of errors? Again, we don't want to ask those questions. We want to ask something different. We can use the same data set, but we want to ask, how can I maybe baseline my asset? How can I baseline down to my process, to my sensors? How can I look at individual components instead of the entire process, basically? So what we're going to do as an example is we're going to look at the bioreactor, and we're going to focus on one component, just the jacket of the bioreactor, all right? And I've got a data set that I'm going to upload here, and this is our offline tool that we can build as many models as you need to. You can upload CSV files, but ideally you'd connect to your data systems and stream data in from your DCS, your data historian, where you can add context and real-time data. For our demo purposes, we're going to go through this on an offline data set. So we're going to say, let's create a test project here. I'm going to upload my data, give it a few seconds over the conference Wi-Fi, and we can see our data set here. So it's a giant CSV with about 200 odd features into it and boatloads of batches of data, all right? What we're going to do is look at the jacket of this bioreactor, and more importantly, see how can we baseline this jacket. I just want to look at something very small and say, I want to understand the ideal operation of this jacket. And then ask another question. Tell me when it's not ideal. Tell me what's influencing it when it's not ideal. What can I do with that information, basically? All right? So it's a very simple thing. I'm going to say my jacket temperature. That's my target column, right? I just want to look at this temperature, which ideally would say what my jacket is, how my jacket is performing, and start to ask more questions on that. So I'm going to go with something we call OneClick Preparation. And this is just a way to get rid of all that data science heavy lifting. Most work in data science, you're spending time in aggregating and transforming and integrating your data sources. We're saying, upload your CSV files, let us take care of that for you. We'll make it somewhat analysis ready so you can actually just go to the intelligence part. Simple as that. So I'm going to let the system do it. And if I don't want to let the system do it, I can do it myself. I can go in, I can change the values individually. I can do whatever I want. Freedom is yours. Choice is yours. So if you think about what we asked, we want to be able to identify the jacket's baseline, right? And then see any detection or detect any anomalies off that baseline. So I'm going to choose and say, let's do an anomaly detection model up top. And now what I'm going to be prompted with is the actual jacket temperature that I chose as my target. So that feature that I said was important to me and I want to ask some questions about that, well, this is that feature. Now, how many of us have a bioreactor in our facility? None. Not bad. It's the first crowd I've ever done that with. But let's just pretend this temperature is all, actually, you know what? This actually works even better for us. Let's pretend we're all bioreactor experts, all right? You can see this. Where should we train? Where should we learn from? What's the baseline? Yeah, right? You need that SME experience. What's the point of having all this if you don't have that SME experience? But let's be naive. Let's squint our eyes a little bit and actually go through with this. I'm going to explain a little bit and say all those little high frequency peaks, these things here, they're just SIP, CIP cycles where the jacket temperature scoots up and down, all right? So what I'm going to do is basically say, let me learn on this when the temperature is constant. I'm going to select these as my training ranges. I can be as meticulous or as naive as I want to. And I'm doing this in a very, again, abstract, naive way because we don't have much of an experience. But if you had, say, batch data, phase data, asset context, all those things, why not just choose and say, I want to look at all my SIP cycles? Well, we could do that with the platform. Once you have that context information, you say, all my SIP cycles, training data. All my CIP cycles, training data. Understand those individual contexts of individual phases. And we need something to test the model. We need something to see, is this model actually working well, right? So I'm going to say, well, let's use this part as our testing range. And just like that, we've created training and test ranges, all right? Again, squinty-eyed and naive. We can be a little bit more particular about this, add a little bit more context, but we'll take it as it is here. What I'm going to be prompted with now is a way to actually score the model. I'm going to be building multiple models, right? I want to see all the different features. I want to see how well we can do it. So what the system is asking me for is, give me a cheat sheet. Let me know what actually went wrong so that I can compare all these models and see which one got it right, basically, all right? If you don't know what went wrong, that's fine. Just choose a random area. We won't even look at that metric. So in this case, we don't know what went wrong. I'm going to say anomaly range. We don't care. We'll move forward with saying what about that data set is now useful. The intelligence is going to parse through that data set of 200 odd variables, and it's going to start pulling out the individual features in terms of mathematical correlation and show those to us and say, this is what we find important. Now, what I've done in this data set is I've prepped it for a few models. So I actually have some models already tucked into the data set. And we won't use that. We'll use that in our second iteration. For now, I'm going to say, well, what about a jacket is important? Ideally, the temperature of the jacket, which is what we're looking at. But what about the things, the components around the jacket? The valves, the steam traps, right? It just so happens that this customer had ultrasound, vibration, temperature around those valves and those drains. So let's see if we can use that. If we look at the list and ignore the first one because that's our model, it's actually listing all the features in your data set that's important. It's going through them and saying, this is what I find the most important. You add your SME knowledge here and you say, this makes sense. It says my vessel temperature is number 2. Makes sense, right? If the vessel temperature goes up, the jacket has to compensate for that. So I'm going to choose vessel temperature, add that into my model. My pH probe in there is apparently very important too. Let's add that in. Looks like my harvest temperature, my valve temperature, this is added in. Again, this is without context. This is when your SMEs, your process knowledge, and your pharmaceutical experts, the people that know and understand the process really well, this is where they come and they shine. They can use the tool, use the data science toolboxes, and really input their knowledge. So I'm just going to build one model for now. And I'm going to say train and validate this model, but we could do as many as we need to. And what it's going to show me right now are 2 charts. The first chart is going to be the actual test range I selected, the latter half of that jacket temperature. And the second chart is going to be my output from the model. So what is my model output going to look like? Well, it's going to take each point in that test range, and it's going to run it through the model it just wrapped. And then it's going to give me a score from 0 to 100. 0 being, this is normal, this is what I've expected from what you taught me in that training range. This abides with it. 100 being, I've never seen this before. What is this? To give you a little context to be able to say, what can I do with this information? Is this actually a fault, or is this just new data that my process has deviated from? So I'm going to say any score that has, actually let's look at the data by itself. Look at the training range. That's our range of data that we said, let's test this model on. Can we notice any anomalies here? Looking at that univariate scale? Can you tell me where the process went wrong? It's hard, right? Here's the output from the actual model itself. It's giving you a score for every point between 0 and 100. And you see most of the points oscillate between 0 and 50, so some normal to a little bit of variation as expected in any biological process. But at certain points, you see a lot of concentration right over here, right? Where this says you're actually hitting a lot more anomalies than expected. So I'm going to say highlight in red all those places where I'm hitting more anomalies than expected. And if we look at that on the actual testing range, this is what it looks like. I'm highlighting points of interest here that are saying these places are anomalous. Why? We can go back through our model and we can look at the individual points in our model and say, well, this temperature went up. Those valve ultrasounds went up, right? So with the platform, we can go through this and basically diagnose a problem and troubleshoot a problem, whether it be real time or after the fact. So let's pretend this information is useful to us. Let's pretend this model actually makes sense to us. What can we do with this information? All we did was basically create some sort of intelligence system that looks at a jacket temperature the entire time, looks at all the core components like a steam trap, your valves, what have you, and says everything's an ideal operation or everything's not an ideal operation. What can we do with that information? Well, this is not AI. This is just a machine learning model, right? We need to build on this. The entire point of AI is not to have one model monitoring everything. The entire point of AI is to build on intelligence. And we're starting from a component level, but we want to take it up to a higher level, right? So let's do something useful with this. Well, I can identify what my current status is in this jacket. Can I make something useful? Can I make a useful decision, like say, what my temperature of my vessel is going to be X hours from now or X minutes from now? Why not? If I know that I'm operating in a normal space, can I actually predict what my temperature is going to be or another probe is going to be X minutes from now? So let's look at that. Let's pretend we're happy with this model that can diagnose good and bad, that can diagnose a baseline and a deviation from that baseline. And I'm going to start another model simultaneously and say, let's build something that does future prediction, all right? So I'll start up a new project. I'll use the exact same data set. And all I'm going to do different this time is I'm going to say, let me actually look at my vessel, because the vessel has a tighter range than your jacket, right? Prepare my data set the exact same way. But with this vessel, I'm actually going to take that anomaly detection model as well and input that into my vessel temperature model. Because if you understand all your components and all your systems on the asset level and the component level itself, you have a better understanding and a better capability to predict where that model is going to be or where that asset is going to operate X minutes or hours from now. So now that we've built that initial first intelligence, let's do a prediction model. And I'm going to be prompted with the exact same thing. I'm going to be prompted with basically, here's your vessel temperature. Looks very similar, but a little bit more consistent. And I can be as meticulous as I need to be, or I can just say, yeah, that looks good. That's my training range. Ideally, we wouldn't do this, but hey, we're at ISPE. And then that's my testing range. So let's see if I can accurately predict that. And let's go, I don't know, 15 minutes out, 20 minutes out. Let's see how I can accurately predict that. So in the exact same way, we're going to get the individual features that come up, ranked in terms of importance to the model. And this way, the users can go in and pick and say, this makes sense, this does not make sense, add their SME context into it. So I'll just take the top few and assume it's good. Add in our anomaly score as well and see how well we can predict this model 15 minutes out. Can we actually have predictive failure? Can we actually predict an anomaly that's coming out? And heads up, yes we can, but with this data set, right? So let's look at this instance right here. What I'm looking at basically is my model prediction, as well as the actual value. It's telling me I'm deviating from my ideal process here. So, sorry, the colors are a little off there, but it's telling me that I'm deviating from my process. Why am I deviating from my process? What about this is actually causing the concern? Well, we can actually go into and look into it, right? This is where we want the SME to actually jump in and start troubleshooting. I'm going to say, let's look at this point and see what the difference is. Well, my model says I should be at 45 degrees for this temperature. I'm at 36 degrees. How do I fix that? Any suggestions? Do I just raise the temperature? No, right? I got to operate within my limits. Well, what we've done here is basically you can see how the influential scores, how the influential values can affect that model. So if you see up here, this is my model prediction for 45, and here's 36. So if I had adaptive control, and if I had full loop control, which I know pharmas, we don't say that around pharma, but if we had that, what could we do? Well, maybe I could look at, say, my jacket, and if I say, drop my jacket temperature down to 40 degrees, what happens? I get a lot closer, right? I get significantly closer. How can I make this better? Maybe down to 35. I'm on the mark now. So instead of you doing this, why not let the intelligence do this for you? That's the unit, that's the idea of building AI with the Quartic platform. And right now we're only looking at a component. Right now we're looking at the jacket itself. Why don't we build an individual piece of intelligence, and we built 2 models here. Why don't we do this for every component of that jacket? The temperature probe, the agitation, the air in and out, the pressure for that bioreactor, right? And now we have intelligence built on an asset. And all these individual things are feeding up into our asset. They're starting from that component level, understanding the deviation of the component, adding to the asset. And then from the asset, you get up a little bit more. You say, well, I don't have just one asset in this process. I have multiple assets. And each asset can look at the process unit level as well, right? I can see all the individual sensors in my process unit and start to predict with a greater deal of accuracy at my process unit level. And then where do we go from there? Well, you have quality parameters, right? The idea with this is now you can learn from your experiences, learn from your intelligence, and maybe start to predict those quality parameters so you can move towards continuous release as well, right? That's the idea with AI, and that's the idea with the Quartic platform. We want to be able to let you build it the way you need to build it, but starting from the ground up in a very methodical way, so that you're not just saying, let me see what I can do, build this, monitor this, optimize this asset, give me better yield, increase it by 1%. You're starting it in a very methodical way saying, I want to fix this one problem, and I know this problem is going to affect everything else. I know this intelligence is going to keep building on and on. So this is our project builder suite, which we have running basically at our booth as well. So if you have a data set or if you want to play with this data set, feel free to show up and you can have at it. We encourage you to bring your own data set. That's usually the best part. You guys show up with your CSV files, plug it in and see what you can see. That's the way to go. And we're doing a promotion with the ISPE basically saying, if you'd like to get your hands on this and just try it out with your data set after the fact, you could definitely reach out to us and we'll set you up for 30 days and you can play with it, hands off from us. We don't talk to you unless you want us to, and see the insight and see your value basically as you need to see it. Any questions? I know I kind of went on really quickly there. Everybody understands AI. Awesome. Great. So guys, if there's no questions, what booth are we at? 105? Well, we can come to booth 105, aisle 100, the cool aisle as ISPE is calling it. And yeah, looking forward to seeing you guys there.